Okay, please interrupt me if there's anything you can't read or don't understand. It doesn't make sense to wait until the end. So today I'll talk about categories and moduli of crystal sheaves. But before I do this, let me recall the picture we had last time and add a few remarks on gerbes. I won't go into gerbes. After that, which I won't talk about sheaves on gerbes. But there's another bit of the theory that I need to tell you. So remember, there was the set of all Azumaya algebras. Remember, so Azumaya algebras were these things that either locally look like endomorphisms or locally free sheaves, and we had a bijection to Brauer-Severi varieties. And the notation was so. For instance, one direction, that's a Brauer-Severi variety, we would get the associated Azumaya algebra by taking the direct image of the endomorphism bundle of this unique extension of the relative tension bundle. Okay, and then there was a multiplicative structure on this thing which did not quite give us a group, but we could turn this into a group by dividing out by the equivalence relation. That gave us the Brauer group Huybrechts, which we, in the good situations, should identify with H2 of Gm, so smooth varieties. And in between, there was the special Brauer group. In the definition, I divided out by special equivalence of molecular equivalence. In particular, there's also this map here. And this, cohomologically, this had to do with H2 of mu n. And since I didn't specify the dimension of the Brauer-Severi variety or the rank of the Azumaya algebras, there's a direct limit here of these groups. And I have a morphism here. And these morphisms from H2 of mu n to H2 of Gm are just the standard morphism coming from the sequence. Okay, and now there's a third interpretation of this group, of this Brauer group, not only Azumaya, not only Brauer-Severi, but this here is the standard theory that goes back to Giraud. This is the set of isomorphism classes of Gm-gerbes. Isomorphism, and these of these individual groups here, that's the set of isomorphism classes of mu n gerbes. I won't give you the definition of the formal definition of a Gm-gerbe or mu n gerbe, but I will give you the examples that I get from Azumaya algebras and Brauer-Severi varieties. So the main point here that's very important is a Gm-gerbe, these are algebraic stacks. But mu n gerbes, they are better. These are the Linear-Mumford stacks. And the Linear-Mumford stacks are essentially varieties. So usually you can do whatever you do on varieties, you can do on the Linear-Mumford stacks. And this is where Liebig works, and it's important. He doesn't work on Gm stacks, he works on Gm-gerbes, he works on on the mu n gerbes, which are Dm stacks. Okay, so let's maybe start with the first example here.
Can you please remind what Bs(x) is?
Say it again? Say it again?
Bs(x).
Bs, oh, Brauer-Severi. All the Brauer-Severi varieties. That's Bs, and that's the Brauer group. SBR, that was the special Brauer group, where I divided out by the equivalence, where I was only allowed to tensor by endomorphisms of bundles with trivial determinant. Okay.
Sorry, I remember the last part is 0, right? Like if I
this was?
Yeah.
Yeah, so here I need an assumption. Yeah, so otherwise I only get the torsion. Yes?
Since we're asking clarifying questions, this TP is the relative tangent bundle, and then this is the canonical extension.
Yes, exactly. So that was this sequence O TP tilde. So this is in the standard situation, that's the Euler sequence, relative Euler sequence.
And TP was the relative over this.
TP is the relative, yeah.
Okay, thank you.
Okay, good. So let's do 2 examples here. So example 1, I start with an Azumaya algebra, and then I associate to it a stack, a gerb MA. So that's a gerb MA. What does a gerb do? So it is a category over X. So I have to tell you where any scheme over X is mapped to, and it's mapped to the set of bundles, so pairs E eta. E is a bundle on T, and eta is an isomorphism between the endomorphisms of E and the pullback of the Azumaya algebra. Is it readable? So I say it again. These are pairs E eta. E is a vector bundle on the scheme T. So for instance, think of T equals X, or an open set of X, and I give myself a vector bundle here, and an isomorphism between the endomorphism of E and the AT. So I trivialize this Azumaya algebra. So the Azumaya algebra over X will not be of this type, but over certain open sets or certain schemes, it might be, and that's the set here. So that's a Gm-gerb, because if you look at the automorphism of this thing, you find that only scaling, only scalar multiplication gives isomorphisms. But there's another thing you can do is, so that's a mu A is a Gm-gerb. So this is another explanation for this arrow going from Azumaya algebras to Brauer-Severi. And you can also look at MA 0, and instead of taking all vector bundles here, you only allow vector bundles with trivial determinant. So the S always was special, so that could be any vector bundle. If you have a special vector bundle, that means its determinant is trivial. And then you get a mu n-gerb associated with the Azumaya algebra. And somehow, if you don't know what the formal definition of a gerb, then just look at this thing and study the example. So in a way, the subjectivity here, which is Gabor de Jong's result, is saying that every Gm-gerb is of this form. Okay, second example, very much in the same spirit. We start with the Brauer-Severi variety and associate to it the gerb MP. Again, so gerb, I have to say what is the category over scheme over X, and very similar. I take all vector bundles on T plus isomorphisms between its projectivization and the pullback of the Brauer-Severi variety. So P is this over X. If I have a scheme T over X, I can just take the product product, I get a Brauer-Severi over T, and I trivialize it by this vector bundle up to isomorphism, of course. And again, this is Gm-gerb. And you can do something similar before. If you want the mu n-gerb, then you put SEB here, so you assume that the term is trivial, and then you get a mu n-gerb.
I think you want the gerb, you don't go from isomorphisms, you keep it.
Yes, that's right, yes. That's isomorphism, yes. Okay. And then there is one last bit in the picture here. Namely, if you think of this as H2 of O star, we could use check homology, description of this as check homology, and represent cycles there by check co-cycles. And so if I take a class in X, I can represent it by a check co-cycle ijk. And then there's a way also to explicitly associate a Gm-gerb in terms of line bundles twisted line bundles, but maybe I don't go into this here. This just makes this thing explicit in terms of germs. Okay. Maybe a helpful interpretation of these germs is the following. So note that for the Brauer-Severi variety, that MP is nothing but, so we start with the Brauer-Severi variety. I told you how to associate a Gm-gerbe, explicitly giving the object of the category. But I can also define this as a quotient. Here, and it's a quotient set, and then the mu-gerbe is divided out by SLN. So Lieblich really works with abstract mu-gerbes and it works there, but in practice, everything we are interested in is actually these are quotient stacks, and that's maybe easier to work with if you're not into Okay. So now this is essentially all I want to say about gerbes, but I felt somehow I have to at least mention them. And later there is, in a way, this language of mu-gerbes seems to be the most natural one.
What the other one's action of GLN on P?
Well, there's factors by the PGLN action. Oh, yeah, so there's PGLN action on P, and you just view this as a GLN action. Okay. Okay, so now let's go to categories. So I'll be talking only about abelian categories, but of course maybe you can derive those and then talk about objects in the derived category, also moduli space of complex of those things. But the first step is really abelian categories. In the end, our moduli spaces will be moduli spaces in certain abelian categories. Okay. So we always give ourselves a Brauer class, and now we represent this only representing the alpha by something else, by Azumaya algebra, by a Brauer-Severi variety, or Kerr cycle. We can talk actually about categories. So if you write the Brauer class as the class of Azumaya algebra, then I can introduce the abelian category of. So this is the category of abelian category of coherent left A modules. So every object in here is in particular coherent sheaf on X, but it comes with it's equipped with an A module structure. Yes. So maybe I put a name to this. So this is in a way Simpson's point of view. I mean, he never talks about this category, but about the corresponding moduli spaces. So this is Simpson's point of view. Let's maybe do an example. If I have, first one remark. If I have any module over A here, then of course the A module structure gives me a morphism from A to E. A always contains OX. It's an OX algebra, and that's just multiplication by scalar. If E is locally free, then this is an injection A into morphisms, and if in addition the rank of E is the square root of the rank of A, then this is an isomorphism. So this is, if you think of A as first easiest case, A is OX itself, and that means when there's an isomorphism, that means this is a line bundle. So this is the case of line bundles over the Azumaya algebra. Okay. Second remark is if A is trivial, in the sense that's the endomorphism of something like this, so you have a line bundle over A, then there's an equivalence of the standard category of coherent sheaves on X with A, with the category of A modules, just by taking any A modules and mapping it to a tensor E. Note, I make this remark a couple of times. if I twist E by line bundle, by proper line bundle, this is of course isomorphic to the endomorphism sheaf of E tensor L for any line bundle, but this equivalence depends on the choice of E. Okay? If I have to compose this and I get. So the important thing is this depends on the not only on A but on the bundle E. Okay. Okay. So the next thing I'll explain how to associate the category of Korean sheaf on the Brauer-Severi writing. Okay, so I start with the Brauer-Severi variety. Second, I represent my class by Brauer-Severi variety. Okay, and then I associate we call this P over X, and that's a full subcategory of P. And what are the objects? All objects P, so Korean sheaves on P, for which the junction morphism is an isomorphism. For this thing. So here P is the projection from P to X, and omega P tilde is, I guess you would guess, the dual of TP. Yes, that's so here I gave you Simpson, and this you should use as Yoshioka's approach. Okay. So as for the Azumaya, well, let's look at the case where we have the trivial Brauer-Severi variety. So let's look at the case where P is the projectivization of a bundle E. F. Then in this case, the cotangent bundle, this extended relative cotangent bundle is nothing but the pullback of E dual tensor OP minus 1, and you get an equivalence between the category of Korean sheaves on X and the category of Yoshioka's category by mapping a sheaf H, I'll put this up, to its pullback of H tensor OP1. So locally, when things are trivial, you get the category you want, as in the category of Azumaya algebra, and this is the way to define the category when the Brauer-Severi variety is non-trivial.
This is the condition and the definition of
there's an isomorphism. So there's an adjunction morphism, and you want this to be an isomorphism. Warning again. Even in the case of a trivial Brauer-Severi variety, this is equivalent to this isomorphic to the projectivization of F tensor L for any line bundle, and the equivalence here will change. So this depends on the choice of F. Why? There's no F in here, but you see the relative O1 depends on the representation of the projectivization So there's a difference. I mean, the relative tautological one of the projectization of F and of F tensor L differs exactly by the L. Okay. Okay, so that's the second way to think about. Here's the sheaves, and now comes the real definition. If you want, I represent alpha by the check cocycle and define the category of twisted Fourier sheaves. So let me just, whenever I write alpha in brackets and parentheses like this, then I mean I fix a cocycle, okay? And I don't have to write these indices I, J, K, which you can read anyway, okay? And the objects here, and maybe here I should put the name, this was first really studied by Calderaro and Esteves. You look at collections like this, so whenever you fix a cocycle, there's also covering by open sets, either in the entire topology or in the analytic topology, and these few pi ij's, they are isomorphisms on the overlap of two open subsets, and the cocycle condition is not satisfied, but it's twisted just by the given cocycle. Okay. One important remark is here, if you fix an E in here, I pretend it's like a sheaf, but what it's really is a collection of sheaves, and it's locally free, then I can define its projectivization by gluing the projectivization of the EIs, and that's the Brauer-Severi variety. And it turns out that this Brauer-Severi variety that also realizes the same class alpha. Realizes alpha. So its class is the alpha. Okay.
You need to explain why these categories are equivalent with different.
I'll come to this. Yes. So we can associate Brauer-Severi variety to any locally free sheaf, but we can also associate an Azumaya algebra to this plus A and E. So of course I can talk about the endomorphism sheaf of E and those endomorphisms glue because of this cocycle condition that will go away on the endomorphism. So that's a property, that's a really non-twisted sheaf, and that's an Azumaya algebra. And these two constructions behave well. You see, I start with a locally free twisted sheaf, I associate Brauer-Severi variety and an Azumaya algebra. Before I told you how to associate an Azumaya algebra to Brauer-Severi variety. And of course, these constructions are compatible. So I put an E in here. And AE is isomorphic to the Azumaya algebra associated with Brauer-Severi variety. Associated with E. Everything works maybe I won't write this, but suppose you find a twisted locally free sheaf of rank 1, then its projectivization, of course, if you projectivize a rank 1 alignment, that just gives you X. So that's a trivial Brauer-Severi variety. So hence the class alpha has to be trivial. And finally, there's the Leibniz point of view, just looking at Fourier sheaves on the mu and Gm. But maybe let's skip this. So the important point in all this was that I didn't give you an abelian category for any given Brauer class. I always had to pick something, either an Azumaya algebra or Brauer-Severi variety or Check-Course cycle, before I could give you an abelian category. And so the next natural question would be whether in the end somehow there is a way to define the abelian category of just the Brauer class. So I'll talk about the equivalences between these categories, and there are two aspects of this. The first aspect is what happens if I pass from one Azumaya algebra to an equivalent Azumaya algebra, or correspondingly for Brauer-Severi or Check-Course cycle. And the other aspect is what happens, what's the link between, so that's Evgeny's question, about these various abelian categories if I switch from the Azumaya point to the Brauer-Severi point. Okay. So let's first talk about Morita equivalence. The first case would be I look at two equivalent Azumaya algebras. For instance, I could look at the case where I just twist my Azumaya algebra by the endomorphism of a locally free sheaf. Okay, and then it turns out these two categories are actually the same. Well, they're equivalent. The equivalence is really given by answering with E, and this is very much like what I told you before, where I just changed this by line bundle. So in particular, here once again, this depends on the choice of E, and not only on the algebra A prime. It depends on E. Okay, it's slightly better, and I'll come back to this, if instead of looking at the usual Morita equivalence that give rise to the Brauer group, I look at only special equivalence, which then led to the definition of the special Brauer group, because in this instance I would only be allowed to tensor by vector bundles with trivial determinant. So I cannot twist by arbitrary line bundles anymore, but only by those that do not affect the determinant of E. So I can. So if this one, so if I want special equivalence here, then I need to assume that the determinant of E is trivial. And if I want to stay in this twist by L, then the L would be a torsion line bundle. I would still have a dependence of this equivalence on the choice of E, but only up to tensor product with torsion line bundles. So there is this dependence, but later we'll see that it behaves better in terms of with respect to stability. Okay, so that's
it's not enough for zero.
Because so if I want to stay in the same special Brauer equivalence, then I need the determinant of both bundles to be trivial, and that means L has to be torsion line bundle. I can't even say of order N. Okay, here comes. So that's the Azumaya point of view. In the Brauer-Severi point of view, suppose I have two Brauer-Severi varieties, P and P prime over X, and that's an observation by Yoshioka. The two categories are actually equivalent. And how is this equivalence given? Well, he says via a correspondence. So he looks at the final product of P and P prime over X. And so you want to go from here to here by some kind of Fujimokai formalism. So you have your variety here, your product, and you put a sheaf on this, and there is in fact a natural sheaf O minus 1, 1 on this sheaf. So that's line bundle on this thing, which behaves as the notation suggests. So it's -1 on the fibers so this is some PN bundle, this is some PN bundle. So also these two projections are PN bundles, and you want it to be O -1 on those fibers and O1 on those fibers. And this one is unique up to tensor product with some line bundle.
10 centimeters.
Okay?
Could you lift the board if you said?
Up to tensor product with L. Okay? So again, there's no natural canonical way to identify, to write down the equivalence between these two categories. It always depends on a certain choice, and the choice can be changed by unique up to tensor product with line bundle. So it appears in all three instances.
The equivalence of P and P prime, so how do you define it?
Well, that means they have the same class in the Brauer group.
It's equivalent to that O -1, 1, and 1.
Right. So if you have this, then you have this, and I think also the other way. Also the so that's actually pretty. Okay. And the last bit is what happens if you pick two different check co-cycles, ijk and let's say alpha prime, ijk. Well, then you know the alpha, the first, or let's say the second one, the new one, is differs by a boundary, and the boundary is a one co-cycle, let's say psi ij. Okay, and then you get an equivalence between these twisted categories as defined before by just taking a twisted coherent sheaf. So that's a collection of these things, and you send it over. So you keep your sheaves, but you multiply your co-cycle phi your gluings phi ij's via this new cycle psi ij. So the phi ij is isomorphism between the restrictions of these EIs, and I can multiply them, of course, these isomorphism with scalars, these psi I. Okay, so that seems like a natural thing to do, but warning that psi, if you know that two co-cycles give you the same class, alpha, they differ by boundary, but the psi ij is not unique. You might change this by an exact closed co-cycle. So what's a closed co-cycle? That's one that defines a line bundle. So you see, I change psi ij by some eta ij, but the boundary of the eta ij is 0. Then the eta ij corresponds to line bundle, and again, this is only unique up to twist by line bundle. So this non-uniqueness is all over the place and can be okay. Any questions? So I explained what happens when you change the representative of the Brauer class. The categories don't change, but the equivalents are not mentioned.
This dx and company prime, so you don't really write without direct sum.
Right. And my recommendation is when you want to prove these things, you get a feeling for those, do it first in the case that you have trivial Brauer-Severi writing, P of E, and then write, I mean, of course, tomorrow I won't remember what to write there, O-1, 1, or O1 -1, and the way to figure it out, write it down. In the case with the Brauer-Severi right is P of E, and then you automatically see what you have to write. Okay. So in each of these three settings, you get a category, which is which doesn't depend on the representative, but only up to non-unique equivalent. And the next question is, can I compare those categories when I pass from Azumaya to Brauer-Severi, or to check? So mix those. So if I want to compare Azumaya and Brauer-Severi variety, I start with the Brauer-Severi variety and get my Azumaya algebra. That was this direct image of the anamorphism algebra of the relative, extended relative tangent, and then I get the equivalence between the Billion category, Yoshioka's Billion category, and the category of AP modules, and the map, the functor is just given by E, F, going to, so I take a direct image of F and twist with omega P, yes. I mean, there's always a question, I'm always confused whether I should put the tangent, but I think it has to be the cotangent, but maybe then there's the dual somewhere. There's an equivalence like this. And the nice thing here is that doesn't depend on anything. Okay, there's no ambiguity in writing down this equivalence. The next would be check versus Azumaya, and that needs an extra choice. So choose, if it exists, a locally free E in the Billion category associated with the co-cycle, locally free. Then we get an Azumaya algebra AE as before, and then there's an equivalence between the two categories. Which just maps a sheaf, a twisted sheaf F to F.
That exists, so there's not the free sheaf, is the covered thing now?
Yes, if you want, yes. Okay. Okay, so that's an equivalence, and also check Brauer-Severi variety. Let me maybe skip this. For this E, the same E, you associate as before the PE, and then you get an equivalence between these two Billion categories. And as before, I told you the AE associated with this twisted sheaf is the Azumaya PE, and all these isomorphisms are compatible. So this is, these two things here are compatible with the equivalence between co-X AE and co-PE. But I cannot.
Sorry, on the right hand side there, this F, it's not actually a sheaf, right? It's a bunch of sheaves.
Right. It's a bunch of.
So how do you get an actual sheaf on the right hand side? On the right hand side, you want an actual sheaf, right?
Right, but the E is also, you see, E has started with a twisted sheaf. Yeah. And then F tensor the dual is an untwisted sheaf.
Okay.
Because in the co-cycle condition, somehow the alpha and alpha inverse, they cancel each other out. So that's an untwisted sheaf. Yeah, that's important. That's an untwisted. Okay.
What's the equivalence between X alpha and E or X? So the equivalence 0.
This one, let's see. What I take is I take the F here. Ah, yeah, that's maybe interesting. I pull back F, so that's a twisted sheaf. The pullback is It's still a twisted sheaf, twisted with respect to the pullback of the co-cycle. And then there's something mysterious. I twist this by OP minus 1. So remark. So the relative OP1 doesn't exist as a line bundle. As a twisted line bundle, where the twist is with respect to the pullback of the given co-cycle alpha. And in particular, that's an important observation here at this point. I told you before, if there exists a twisted line bundle with respect to some co-cycle, that means the class of this co-cycle has to be 0. And that means if I pull back alpha as a Brauer class on the Brauer-Severi variety, this thing is actually true. So once again, I pull back a twisted sheaf. That remains a twisted sheaf with respect to the pullback of the co-cycle. That's a twisted line bundle, twisted with respect to the pullback of the inverse of this thing. And so the tensor product is an honest, untwisted sheaf, and I think there's an object in there. Okay, so now I'll switch to stability conditions and moduli.
So I think that so if the cycle is triggering the Brauer group OP, that is untwisted equivalent to an actual number.
Yeah, so I can write down the equivalence to the category of coherent sheaves on X, but this equivalence would not be unique. There's no distinguishment. I mean, I'm a little cheating when I talk about these co-cycles. I pretend that some of the only way to change this co-cycle is by staying on the same open covering and change it by the boundary of something. Of course, I also have the option somehow to reduce, somehow to make my open covering finer, and that you have to do, of course. Okay. Yes. So here I showed that this is contained in the kernel, but in fact you can show that the kernel is generated by this alpha. Okay. Stability and moduli spaces. And again, I follow the same pattern. So there are various ways of talking about these things, and one for each setting. So let's start with the Azumaya setting. So we give ourselves an Azumaya algebra. So again, yeah, maybe I should say this. Azumaya algebra on X. So here you have to say, well, I tell you now, as a special case of general construction of Simpson, and then there's a paper by Hoffman and Stuhler. So this works now for varieties over any algebraic closed field. So you look at polarized projective variety, OX, and then you look at, we want a stability condition for this category. Every object in here is in particular a coherent sheaf on X, and we have the natural stability condition here. So that I guess you all know this. So an object here is stable, so E is stable, then only if it's pure, and for all sub-objects, you want this inequality where I take the Hilbert polynomials of E and F, divide by their rank. So it's pure if I'm in a partial-free case, so that this is really nothing but the rank. If I'm in a pure case, this R of F or R of E are roughly the leading coefficients of the Hilbert polynomial, and you want this inequality for large. I guess you all know this pretty well. And then in a way you just pull back the stability condition here. You require this condition, so you require the purity, and you require this condition only for sub-objects in here. Okay, so pull back gives a stability for A modules. So we only consider A submodules. So this is in one of Simpson's very early papers on moduli space of representation, part 1, because from DHS. And this, in his context, this runs under the name of lambda modules. He was not interested in Azumaya algebras, he was more interested in Higgs bundles and things. So he talks about lambda as a ring of differential operators. But this is some of the Azumaya algebra cases, the easiest case, situation. Okay, and his theorem then, so he proves this over C because of boundedness issues, but work of Langer then later fixed this, and this is what Hoffman and Strudel then did. For fixed polynomial, let's call pi, there exists a coarse moduli space M. So we have to put the Azumaya algebra and the polynomial of semi-stable A modules E in O XA with Hilbert polynomial pi. Okay. So those moduli space exist. The geometric points are parameterized as equivalence classes. There is something strange in his theorem. He says they are only quasi-projective moduli spaces, but I think this has to do with because he's looking at very general lambda rings. For Azumaya algebras, they're actually projective. And the stable ones form an open subset, which then parameterize really the isomorphism. Okay? So there's nothing unusual. I mean, for everyone who's seen moduli space of stable sheaves, as you probably all have, this is a very natural thing to do. Of course, technically there's something to do with boundedness and DIT and stuff, but in the end you have this result. And now we can do the same. We try to do the same thing in the Brauer-Severi setting. So we start with the Brauer-Severi variety, and this is what Yoshioka does.
Sorry, the moduli not
there's a subtlety which I haven't really understood. In Simpson's paper, he only produces moduli space that are quasi-projective, but my understanding is this has to do with his assumption that he works over very arbitrary lambda rings. In our case, we have Azumaya algebra, we have components of moduli space, so they are actually. And so Yoshioka, so he defines stability notion for objects in this category. But it turns out, and this was, I think, then later pointed out to Leibniz, by Leibniz to Yoshioka, namely that this is just Simpson's stability condition under the equivalence. This is Simpson's stability under the equations. So Simpson's moduli space, special case of Simpson's moduli space gives you Yoshioka moduli spaces.
And those equivalences, when you replace A by equivalent one, is it clear that it's the same?
Okay, this is an interesting question. I'll discuss this. Okay. That's the next one. So that's the next obvious question. How to compare the stability notion under those equivalents, and that's a big warning. Stability is in general not preserved under OXA. This was the equivalence where we met H, BH, okay, so that's a problem. Let's look at the easiest case. We write A, so we assume A is just OX, which we write as an homomorphism of some line bundle. Okay, and then this equivalence we constructed is given by tensor product with a line bundle. Okay, and 20 years ago, there was a time when we thought, of course, stability will be preserved by this operation, and then actually Yoshioka and Ellingsuit and Goethe, they discovered that's not true. There's no reason, if you write down the Hilbert polynomial, there's no reason why this Hilbert polynomial inequality should be preserved by tensor product in L. So this does not respect Giesecker stability, but it does preserve, it preserves mu stability. If you think of torsion-free sheaves, the mu stability is defined in terms of the first Chern plus of the degree, and twisting by line bundle, you control exactly what happens by tensor product with line bundle with the slope, the degree of the bundle, and it just in the stability inequality, it comes in on both sides by the same amount, and so the mu stability is unaffected. So what we have is, if I have Azumaya algebra, I fix myself a Hilbert polynomial. So this is one of Simpson's moduli space. Then I go to an Morita equivalent line bundle for Azumaya algebra, for instance, one of this type. Then, of course, under this equivalence here, the Hilbert polynomial changes, but that's somehow, this is something you fix once and for all, such that this is kind of a H, or So this you fix once and for all, and these two don't have to be isomorphic. At least some of the natural equivalence doesn't give you an isomorphism. But if you look at this at the mu stable ones, so this is typically an open subset, they are naturally isomorphic. They are naturally isomorphic. And I can even say a bit more if instead of looking at Brauer equivalent Azumaya algebra, I look at something that is with the same class in the special Brauer group. So if A prime is special equivalent, so their classes are the same in the special Brauer group, then chi is actually equals chi prime. So then you see what I do here is yes, because you see, you can, for instance, if I replace A prime by A times n E prime, but the two differ by line bundle by torsion line bundle, then the Hilbert polynomial will not change. If you look at the Riemann-Roch formula, you change something by a torsion line bundle, it comes in by its Chern class, but that doesn't affect the Hilbert polynomial. So that's why the chi and chi prime will be the same. Okay. Now I wanted to talk about P services. Maybe I don't rush this. I do this on. Okay, I'll stop here.